Good morning. How are you all doing this morning? So, today we are going to study electronic effects. Electronic effects, as you all know, is a very important primary basic uh, effects which are compulsorily required to study the mechanisms of organic reactions. I cannot limit them to only organic reactions. Certainly, some of them have a very important applications in even understanding the inorganic mechanisms also. So, let's start with our today's topic, that is electronic effects. Now, what is electronic effect? Basically, electronic effect is movement or displacement of electrons. It could be a temporary displacement, it could be a permanent displacement. Whichever type of displacement, if is present in a particular type of molecules or set of molecules, then they, if studied, are named as electronic effects. Okay, they could be of two types. Electronic effects could be of two types. Electronic effects could be of temporary type and the permanent type. Temporary, when the particular effect is generated or is created under the influence of certain external species or surrounding, but are absent or reverted back if those surrounding or external species are removed. Such effects are called temporary effects. Example is the electromagnetic effect. We are not concentrating much on these effects, just a general. See, for example, if I bring an electrophile close to this alkene, this otherwise non-polar pi bond will start polarizing such that it can form an attractive linkage towards incoming H plus or towards the surrounding H plus. Just an example, say this way. Now, these are the complete bond fission and formations, but if I could take them as this del plus, H del plus, this bond has started forming, this bond has started breaking. If at any moment during this particular stage, if I remove H plus, okay, if I remove this H plus from the surrounding, immediately this bond will break and a double bond will be formed here. So it is reverted back if I remove the H plus from the surrounding. The polarity distribution of this del plus types is not the characteristic of alkenes. It is not the characteristic of the molecule. It is generated in presence of certain surroundings. Such effects are called temporary effects, electromagnetic effects. Okay? If if the effects are permanent, that is the property of the molecule, they are not coming and going, appearing or disappearing in the presence of certain environment, temperature, pressure, medium, etc., then such effects are called permanent effects. Okay, permanent effects are the one that we have to concentrate and should know more about. Okay, these are the one which are more important. So let us study which are the permanent effects. Well, permanent effects like inductive effect, resonance, hyperconjugation, aromaticity, steric inhibition of resonance, steric inhibition of protonation, etc. There are so many types, but let's start with inductive effect as a starting point. This is the most simple effect, I would say. Inductive effect is the most simple, most effect. Now, what is the inductive effect? Well, inductive effect is the polarization of a non-polar bond Polarization of a non-polar bond in presence of some polar bond in the vicinity is called inductive effect. It is an induced effect. A very usual, very common example which you all come across is, say, this. Now in this there is del minus and del plus. Okay, there is this del minus and del plus. So this bond is a polar bond. This bond is a polar bond. But these bonds, let me mark them with other color, say blue. These bonds are non-polar bonds. Okay, these bonds are non-polar bonds. But as an attractive electronic wave due to this electronegative chlorine has begun in this bond, its effect is observed in further bonds also, and these, though it diminishes with distance, as we move further and further, if it definitely diminishes with distance, but there is certainly an effect. Okay, and this is what is called electronic inductive effect. To be very practical, if I say practically, it should be neglected. I cannot say it is absent. It should be neglected after, say, 3 to 4 sigma bonds from the source bond. We are just saying it should be neglected, though it is always present. You cannot say that it is absent. It is there, but practical negligence. Now, there are two types of such inductive effects. A, whenever there is a movement of electron, it could be always of two types. One, you are pulling the electron towards yourself, and other, you are pushing the electrons away from you. Okay, so there are always two types of electronic effects. One is plus I, that is when you are pushing the electrons away, and other is minus I, when a group or a particular species is attracting the electrons towards itself. Okay, and the relative parameter of these plus I and minus I are always with comparison to this carbon hydrogen bond, are always in comparison to this carbon hydrogen. See, for example, in a carbon hydrogen, the shared pair of electron is placed over here. So if I want to compare or comment on this G group, whether this is a plus I or a minus I, so relative to this position, if electrons are more towards G, relative to which position? Related to electronic position between carbon and hydrogen. If they are more towards the G, then G is called minus I group. And if it is more towards the C, then G is called plus I group. If the electron is towards the G, then G is attracting the pair, so it is minus I. You can relate it very much like a normal electronegativity and positivity. We use the word electronegative when electrons are pulled by a certain atom and pushed. When it is pushed, then we call it electropositive. Now, this is the order which has been derived after studying several possible molecules and bonds. This is something that, if possible, please remember it. That gives you speed and accuracy in questions when you are appearing in any of the final exams. It could be a NEET, it could be a RIT, it could be a mains, MSET, any exam if you'll appear. Time is a very crucial factor. At that time, in that limited amount of time, when you have to do physics, chemistry, and mathematics, all with almost an equal expertise. You cannot, at that point of time, sit and try to remember what was being told, what was the order of these groups in minus I. So, if possible, please literally learn them. Just go through them and learn them, that order of the minus I is this. Some of the important that probably, yeah, you must have already in your memory is NR3 plus, NF3 plus, NH3 plus, NO2. These are, I would say, more important that we need to remember as compulsory. You may compromise on those which I didn't underline, but please remember those which I did underline with the red. As far as plus I order is considered, please remember all, and it is not much, it is not that big also, so you can remember. Now, rules of inductive. What are the rules? The rules, what I mean here is how you will apply the effect when you are doing some questions. Always remember, as I told while introducing the inductive effect also, that inductive effect is inversely proportional to the distance of from the polar bond. Okay, it is inversely proportional to the distance from the polar bond. More away we move from the source bond or source atom, the effect of inductive goes on diminishing. And as we said before, practically can be neglected after four bonds and further. Second is, I effect is directly proportional to the number of groups. What do I mean by number of groups? Well, this is the application. Let me tell you. For example, yesterday we studied carbocations. If I say that CHCl2 and CH2 plus CH2NR3 plus, if I'm asked to compare stability of these carbocation, as I have taken the groups as minus I, and carbocation stability C plus stability is inversely proportional to presence of electron withdrawing groups. If these groups are increased, stability will go down. Okay, so now here I have a group which is a very strong minus I group. Here I have group which is not strong, but the number is more. They are 2. So for such conditions, I am saying number of groups dominate over power. Dominate over power. This will not have as much of minus I as this could be. So if I am asked which is exerting stronger minus I, my answer will be 2-chlorine. And thus the stability is the second one greater than the first one. Okay, so you have to consider these whenever you are solving a problem. First, the effect will diminish from the distance if you move further and further. And second, if you have to select between the number and the power, then the usual observations always suggest that the number of the groups dominate over the power of the groups. Okay, so let's move further. This is a very important effect, resonance effect. If I could have had a lot of time discussing resonance, this is one of my favorite lectures, I would say, resonance effect. Resonance effect has been described by certain scientists, very renowned ones, that it is it is the biggest lie in the organic chemistry, but is so important that you cannot move even a step ahead without knowing the concept of resonance. It is so very important. Okay, so someone very renowned in the world of organic chemistry has said these words, that it may be the most uh, unreal phenomena, but it is the most important phenomena to study and understand the organic reaction mechanisms. So, we need to know the rules on which or using which we can draw the resonating structures and comparisons. So, resonance effect. It is also known as a pi electron delocalization or delocalization of pi electrons. Now, see, I am using word pi electrons. When I say pi electrons, I include pi bond, I include lone pair, I include negative charges. If I have positive also, positive charges, but the positive charges will not have any electron. It is rather an absence of electron. So when I use the pi electron, I include all these wherever possible to participate in the resonance. Okay. Now, rules for writing the resonance, how you draw or what rules you need to follow while drawing the resonating structures. Okay. So there are certain very basic rules that we need to take care while we draw the resonating structures. Okay. And those rules that we need to remember while drawing the resonating structures are: first, all the canonical canonical forms, that is also called the resonance structures, should follow Lewis dot structure. Okay, I'm not going to discuss them much, just going through surface. Position of nuclei for all the atoms should be same in all the RS. Number third, all atoms participating in resonance should lie in same plane. I'm not saying the complete molecule has to be planar. Only those which will participate in resonance should be in the same plane. This is for the maximum overlap. The purpose of this rule is for maximum overlap of p orbitals. Okay. Next point is all canonical forms must have same number of unpaired electrons. While you are drawing the structure, it should not be that one structure is having zero unpaired electron and in the another structure you end up drawing two unpaired electrons. If I'll draw this will be taken as wrong. This is not the canonical structure of 1,3-butadiene. Okay. Point number next is all structures should be of nearly same energy. There should not be vast differences in their energy. One is very stable, other is very unstable. No, it should not be like that. And energy, this is always a rule, huh? Energy of actual molecule is always less than energy of any resonating structure. right? That is a very important point. That is why resonance is a stabilizing phenomenon. Okay, is always energy of actual molecule is always less than energy of any resonating structure. Whichever we take, it is always going to be less in terms of energy. Hybrid is always going to be more stable than any of the RS. Okay. Number next is I would like to write in a short, so reframing canonical structures contribute unequally towards resonance hybrid. More stable, more contribution. Okay. So these are the general rules that we need to follow while we draw the resonating structures. And just on the basis of these rules, once we learn how to draw resonating structures, once we learn, say for example, in case of benzene, these are the resonating structures, hybrid. Okay, in case of butadiene, the resonating structure will be plus, minus, or it could be plus, minus. Hybrid of the three will be taken as, and there is no charge. Okay, now I can also have other structures. For example, I want to take one example from NCRT in organic chemical bonding chapter, that as all atoms are taken as a separate nuclei, don't get confused that it is ultimately the oxygen only uh, which is bearing this minus charge. So what is the difference? Okay, so what is the difference? The each atom of oxygen, you treat it as a different nuclei. So they are all different entities, and the structure which is having negative on this oxygen will be regarded different than the structure having zero charge on this oxygen. Okay, so when all the contributing structure are exactly similar, then they contribute equally towards the hybrid and are called equivalent resonating structures. But if they contribute unequally, some are charged structures, some are neutral structures, then they are called unequivalent resonating structures. In case of benzene, we use sometimes equivalent resonating structures because the contribution of Devar structures is neglected. So you can go for that thing, and sometimes the bond data also supports those. In 2015, a direct question, the number of resonance structure for N was asked. So first let me tell what this N will be. N will be the anion. This question has made us think that we shouldn't be very, I would say, we should be very comfortable in drawing a resonating structure, a fluent while drawing the resonating structure of different molecules. Because they could even ask how many number of resonating structures are there. In case of cyclic, always you repeat each and every possible structures till you come back to the original structure. Okay, so if I may start, the original given structure So my second structure minus here double bond. You have to go on repeating the whole process until you come back to the same structure. Now here I can have two directions. Now one is if I go this way, this can further go to this. If I would have moved from here to left hand side of the ring, then it would have been like this. Okay. Till I reach my original positions I'm drawing. Is it okay? First, I hope you have got the general idea, correct? And similarly, you can definitely draw one more structure. Search and draw. I have told you the hint. This is how you need to move on with your structure. Once you move continuously, you learn, you will get the idea. Hmm? For example, I think I should have a little change here. And after drawing the complete structures, just go through them. That is there any structure that you have repeated? In case if there is a repeated, it will be counted only once. Okay, so this is how 2015 JE question was there, and you can expect such questions anytime in these integers. Okay, so we have learned how to draw the resonating structure. Next is the fact number next. As I said, if they are equivalent, if they are of same energy, then they will contribute equally. But if they are unequivalent resonating structure, then they will not contribute equally towards the hybrid. Okay, then they will not contribute equally towards the hybrid. Then what is their contribution? How do they contribute? As we have said, that they contribute in the relative order of their stabilities. So, what is the, excuse me, what is the relative order? How to decide the relative stabilities of resonating structures? Okay. Now, of course, a very important fact in this is certainly experiment and intuitions of the chemist. But still, the rules that we can devise are always as a rule structure with more number of covalent bonds are more stable, because whenever there is a bond formation, there is release of energy. Whenever there is a bond formation, there is release of energy. So if we come across a structure with more number of bonds, it is definitely more stable. Neutral structures. Neutral structures are more stable than charged structures. Neutral structures are more stable than charged structures. Okay. Now stability is further decreased. Stability is further decreased if if there is increase in charge separation. Okay, plus charge minus charge. If they are far apart, if they are separated apart, then it is going to decrease the stability of a particular resonating structures. Okay, structures with more formal charges are also unstable. More the number of charges you create, structure becomes more and more unstable. Okay, as in this direction, I can say structure with more than two formal charges usually will become very unstable and will contribute very little towards the resonance hybrid. Okay, and for stability, we'll have to follow just the reverse of this. Point number 4, if I am studying the charge structures amongst the charged resonating structures, if negative charge is on more electronegative atom and positive on less electronegative atom, then it is more stable. Then it is more stable. Okay, if structures with distorted bond angles, if you draw such distorted bond angles, structures with distorted bond angles are bond angles and even bond lengths, if you draw random, then they are unstable. Then they are unstable. Now, these are the usual factors while comparing the relative stability of different RS that we need to take care. Okay, while drawing the structures of a molecule resonating structures, right? Once we go through this stability of different RS, let me tell you one more factor, that a positive charge on electronegative atom on electronegative atom with octet complete is stable and allowed, but with incomplete octet not allowed. Point number 7, positive charge adjacent to second period electronegative atoms having lone pair is more stable than away. Now, these two are not usually mentioned in your notes and in your books, whichever you refer. But these certainly influence the questions. Let me tell you where it influences. See these two questions which appeared at different times in J. Let me start from 2007 one. In 2007, among the following, they have asked which is, I hope it is very clear to you now, which is the least stable of all. Okay, so we have to find the one which is most unstable. As soon as I read this, First, I will check the charge, number of charges in each. So this has 2 plus 2 minus, 2 plus 2 minus, 2 plus 2 minus, 2 plus 2 minus. No point of difference. Now I'll check the number of bonds. Sigma certainly will be same. I can see the number of bonds in all the four is 2 pi bond. The only variation in resonating structure is a pi bond. So all of them have a 2 pi bond. That is also not of much difference. Now I'll think about the charge positions, the charge placed. है ना? So if I could see the relative charge positioned, I can see in A the 2 plus charge are placed exactly adjacent to each other. So they definitely will create a lot of repulsion. Here it is quite a good setting of plus minus alternative. So attraction is there. Plus is far away. It seems to be stabilized. Plus minus. So answer is A because the similar charges are placed closer, causing repulsions. Moving to 2008, C, continuous 3 years, the question came. The correct stability order for the following species, though it was a carbocation question, but the factor which was used was certainly a resonance here also. How a resonance effect, I told you that a plus charge close to an atom from second period will have a very strong stability. So this will have a complete octet resonating structure. So will this be. So, despite the fact that these plus charges are close to oxygen, but they are very stable, they are more stable than second and fourth because of the resonating structures having complete octet or more number of pi bonds. Now, in first and third, both we are having a complete octet. So, the difference is this is a 3 degree and this is a 2 degree. So, one is going to be more stable than third. And then 2 and 4 are decided on the basis of inductive and hyperconjugation. Okay, so it is a 2 degree carbocation, it is a 1 degree carbocation. So 2 is more stable than 4. Answer given was D. Somehow resonance was also involved in this. 2009. Again, the correct stability order of the following resonating structures is asked. Diazomethane is in the question. Now they are again asking relative stability. The factors that we just studied, we have to apply those. First, I'll think about which has the more number of pi bond. Let me write here my sequence of thought. I'll say more number of pi bonds. I can see first and 3 are in competition because they have 2 pi bonds, whereas 2 and 4 have 1 pi bonds. So definitely 1 and 3 are going to be more stable. Then I'll compare charge number, how many charges are there. So all have equal 3 equal to 4, no point of difference. Then charge atoms, whether the charge is on electronegative atom, negative charge or positive charge is on electronegative atom. Comparing that, I can say 1 is more stable than 3. Okay, so that is our first criteria, that 1 is more stable than 3. And on the similar criteria, I can also differentiate that second is going to be more stable than 4. Why? Because in second you are having plus on carbon, okay, with incomplete octet. Whereas in this you are having plus on nitrogen with incomplete octet. So our answer is very clear that 1 is going to be more stable than third, then 2, then 4. 1, 3, 2, 4. Answer given was B. Okay, so whatever we just covered till now, there have been direct questions on these two concepts. Okay, so let's move further. J 2005, which of the following resonating structures of 1-methoxy 1,3-butane? Oh, least stable is being questioned. We have to find the one which is going to be the most unstable. So again, our approach is same. First, I'll find the number of pi bonds. This has 2, this has 2. So they are out of my race because they are having more number of pi bonds. I cannot have them as stable. Coming to C and D, we just did plus close to a lone pair site. Is this will act as a minus charge. So this will be more neutralized. So C is the most unstable structure. Okay, so moving further, SIR, steric inhibition of resonance. Okay, this is a very basic condition, that is for a molecule to be able to resonate completely, or the part of the molecule which wants to participate in resonance should lie in the same plane. Now, if for whatever reasons the molecule loses its planarity, then definitely that part will lose resonance. If, say, these three G1, G2, G3, G1, G2, G3 are bulky, are big, then they cannot be planar. They all cannot be in one plane. Then they all cannot be in one plane. One has to move outside, one has to rotate. So, usually it is the middle one which rotates. And when it rotates, its pi bond also moves out of the plane, and thereby it is the G1 which suffers steric inhibition of resonance, SIR. Okay, now in a very conclusive statement, I can say that if G1, G2, G3 are, let me have some examples of this type of groups: iodine, NO2, COOH, COOR, pH, COR, NR2, NHR, okay, SO3H, SO3R, SO2R, CH double bond CH, COOH, etc. What I wanted to emphasize was that they are all bulky, that they are all big. Okay, a combination of all three could be same. It is a possibility that all three are different. Okay, then G1 will suffer SIR. Then it will be having no resonance with the ring. If G1 is from above list and G2 and G3, or any one, G2 and G3 is alkyl, then also G1 suffers SIR. Okay. Point number next. If G2, G3 is from above list, but G1 is from following groups, then no SIR on G1. Remember these groups: F, NH2, O minus, OH, okay, CH triple bond, CH ni C triple bond CH, Sino. Okay, these are the groups that do not suffer any SIR, despite the fact that the adjacent groups are bulky. Okay? Now, what is the effect of this SIR if there is present? If an SIR effect is present, let me have one example. For example, if I'm told that iodine, NO2, NO2, iodine, say NO2, NO2, bond length A, bond length B. The question is compare bond length A versus B. Answer is A is longer than B, because here this iodine will suffer steric inhibition of resonance. Okay, steric inhibition of resonance, and so it will not have the double bond character with the ring. It will be just having inductive effect but no resonance effect with the ring. Whereas here I is free, its adjacent atoms are small h. So here it will have a resonance effect. As a result of that resonance effect, here double bond character is created. Double bond character is created. Due to that double bond character, this will become smaller as compared to A. Okay, as compared to A, it will become smaller. So that is SIR. Next, we move to something called resonance energy. I'll not take much of its calculations, just a definition. Resonance energy. Now, resonance energy cannot be calculated directly. Why? I'll tell you. First, it is a stabilizing energy. It always stabilizes the molecule. Okay, it always stabilizes the molecule. Resonance energy. It is the difference of energy between most stable resonating structure and resonance hybrid of a molecule. Now, resonance hybrid is a real entity. Resonating structure is imaginary. So, when you have to find the difference between the two, but one of the entity in that difference taken is an imaginary species, then certainly you cannot find any direct method for its calculation. We have to go by indirect method. Okay, we have to go by indirect methods. Indirect methods, so resonance energy will be calculated indirectly using heat of hydrogenation, heat of formation, and heat of combustion. There will be separate lecture for this, maybe in the T1 series of a teaching tomorrow. So heat of hydrogenation, heat of formation, heat of combustion. So we have to calculate it indirectly. But as a convention, but as a convention, it is always written with a negative sign. You always have to represent your resonance energy as a negative sign, as it is the amount of heat released. We consider it as the amount of heat released because it stabilizes the molecule, and so is always written with negative sign. But when we are asked to compare resonance energy, usually we only have to compare their magnitudes. Benzene will be said to have more resonance energy with say value minus 36 kilocalorie per mole Then hypothetically taken furan resonance energy to be say 12 kilocalorie per mole. So minus 12 versus minus 36. So benzene will be said to have more resonance energy as it is the amount of heat released. Okay. I'll just quip fastly to there are two types of resonance. One like inductive effect plus R when the groups which can donate a pair of electrons, say halogens, OH, for that they have to have a lone pair of electrons. Okay, OR, NH2, NHCOR, etc. Minus R when they don't have electrons and they attract electrons towards themselves. Okay, CH3, CH2 plus, CH2 plus, NO2, CO, NH2, etc. Then these are minus R groups. There are certain groups which can exhibit both plus R and minus R depending on the condition with which, depending on the group with which they are attached. Benzene, vinyl. I'll, oops, it is gone. Okay. NO, it has lone pair and pi bond. SO2OH. C sulfur has a lone pair as well as a electronegatively bonded pi bond. So they are all minus R or minus R, plus R capacities both. And always remember the word mesomerism you can come across. It is also almost synonymous to resonance. There are some minute differences, but yes, you can take it almost synonymous to the word resonance. Okay, so now let us move to next concept, that is hyperconjugation. Hyperconjugation, other names of hyperconjugation are, it is known as Baker-Nathan effect in the respect of the scientist who initially did contributed a lot in developing the concept. It is also called no bond resonance, sigma bond delocalization, sigma pi resonance. These are the other names. Okay, the rules for writing the hyperconjugative structures and the relative stability studying structures are same as that of resonance, except the fact that now we are allowed to move to break the sigma, though we will not move the atom here and there. This H is taken here itself. You cannot move that H, but yes, you can break the sigma bond. Okay, so when you can break the sigma bond but cannot move the atom, then it is called hyperconjugation. The word no bond resonance came because if you see in the different resonating structures of this molecule or hyperconjugative structures that I have drawn, there are such structures where there is a no bond condition between certain atoms. So it is also called no bond resonance. For hyperconjugation, we always are bothered about how many alpha hydrogens to a carbocation or a radical or wherever you are studying is there. More the number of alpha H, more the number of alpha H, more will be hyperconjugation. And also remember CD bond also can show hyperconjugation. Though with increased bond energy, its effect will be less. What do I mean? That if I have a CD3 whole thrice C plus and CH3 whole thrice C plus, then yes, both of them will have hyperconjugation. Okay, both will have hyperconjugation. Both will have hyperconjugation. But CH will have more effective hyperconjugation, more effective H effect. As a result, the order of stability is like this. If in a condition there is an equilibrium between these two carbocations, then CD3 converting to CH3, the K equilibrium is found to be a 1.95, 1.97. That shows that the CH3 one is more stable than the CD3 one. Okay. Now in 2008, a question came, hyperconjugation involves overlap of the following orbitals. If we see, hyperconjugation is found in case of alkenes, in case of alkyl benzenes, in case of radicals. Okay, alkyl benzenes, radicals, carbocation, carbocations. Correct? In all of these, somehow there is the alpha H which is involved. So one is always the alpha H1 bond, that is the sigma bond is there. Okay. In case of alkenes, I'll just draw basic that this is the p orbital, this is the sigma. They'll overlap here, na? So there is a sigma and p. In case of alkyl benzenes, also there is sigma and p. In case of radicals, that unpaired electron placed, in case of radicals, that the hyperconjugative structure, the hyperconjugative structure is CH2 double bond H dot. So see this sigma and this unpaired p overlap. So here also can है तो ये sigma p ही. Carbocations I just drew. Here there is sigma and empty p. So considering all the usuals, we have got that hyperconjugation involves the overlap of sigma orbital with p orbital. Now that p could be filled, could be unpaired, could be empty, but it is overlap of these. In 2008, this was a question. Now moving to 2011, number of contributing structures showing hyperconjugation involving CH for the following molecule for the following carbocation is. Okay, so considering how many different resonating structure, hyperconjugative structures I can draw. So as you know that for that we need number of alpha H. And they have clearly indicated involving the CH bond. So the one that is drawn is to be excluded. Alpha H to this carbocation, encircle the carbocation. All carbons connected to this carbocation will be named alpha, and all hydrogens attached to these carbons will be named as alpha hydrogens. Okay, so how many alpha hydrogens I have? I have 3, 4, 5, 6. I have 6 alpha hydrogens. I have 6 alpha hydrogens. So involving CH bond, answer has to be 6 because there are 6 alpha H which can participate in this particular resonating structure, hyperconjugative structure. So there will be 6 uh, structures, contributing structures for this particular molecule, this particular carbocation involving the alpha H. Okay. Moving to one more question which came in 2013, which shows the hyperconjugation stabilities of third butyl cation and 2-butene. Okay, third butyl cation and 2-butene respectively are due to. Now this is quite specific as compared to previous one. Third butyl cation is this one. This is our third butyl cation. Let me draw it completely. This is our third butyl cation. How many alpha H I have in this structure? I have 9 alpha hydrogens here. Okay, I have 9 alpha hydrogens here. So when this sigma will overlap, this p is empty p orbital. Correct? Is due to the movement of electron, the delocalization from sigma to empty p. Okay, observing this only, I can say that sigma to p filled and empty p. This seems to be more correct because they have used the word, I think, respectively. So first we have to answer for third butyl cation, then we have to answer for 2-butene. Okay, so 2-butene. Let me go to 2-butene. Now, in case of 2-butene, this structure, this pi bond, is already a bonding molecular orbital used. It is a pi bonding molecular orbital electron. Now, this bonding molecular orbital electrons or this orbital is already filled. Okay, so when this sigma wants to hyperconjugate like this carbon has to offer its anti-bonding molecular orbital only available to accept the incoming pair of electron from the sigma. It cannot accept in its bonding MO. This star, the word star symbol is taken as anti-bonding molecular orbital. Resonance as well as hyperconjugation are based on molecular orbital theories concept only. Okay, so this sigma electrons will move to pi anti-bonding molecular orbital. Then only you can have the hyperconjugative delocalizations. So the answer is A. Is that okay? So this was the one which was asked in 2013. Application of these effects is very vast. In the coming lectures, we are going to deal with its acidity-basicity concept, but please revise aromaticity as a very important application of these effects, as there are questions which come directly on this particular concept, that yes, which of the following are aromatic, anti-aromatic, or non-aromatic. So just go through that. If you have any specific problem dealing with the questions which I could be of any help of, you can definitely post on Sri Chaitanya Educational Institutions Facebook page under my video. I'll keep in touch with that page, and if I could answer them, if I could find them relevant, I'll surely would like to incorporate them. I will answer them in my coming lectures. But for that, you have to go through the complete video of our lecture and then study your notes and NCRT. Okay, so this is your today's target. Please complete that work and we'll meet tomorrow for our next lecture. Till then, goodbye everyone.